Topic 22, differentiable. So the definition of a differentiable is a property that is possessed at x is equal to c if the derivative at that point exists. Okay? So if you have a function that's not continuous at x is equal to c, then you can also say that this is not differentiable at x is equal to c because it's discontinuous. So if you have a discontinuity, then it's also not differentiable at that point. Another one that may not be so obvious to you is something that looks like an absolute value. So if you have a function that has a sharp turn in the function, then it's not differentiable because the right and left hand limits are not the same. So notice, for example, the slope of this line right here is -1. Okay? Now the slope on this line over here is +1. Now as you get closer to this one, now at this point, you really don't know, at this specific point, you don't really know if the derivative from the right and the derivative from the left is the same. Okay, so that's how that works. So again, basically if you have a sharp point, then it's not differentiable at that point. Okay. Now on this one. Now this is just an example. I'm not going to do it on the calculator, but this is the same idea. If you're to zoom in on this, say you have some kind of cubic function, you're zooming in on that little window. The more you zoom in, it's going to look like a straight line eventually. Now on the other side, if you have something that looks like an absolute value like this with a sharp point, the more you zoom in, it still looks like a sharp point. So no matter what you do, you're never going to have a curved line. Now I think that would be the opposite. If you had something that was more curved, or if you had something that was more curved and you were looking at this window, well, eventually you would be able to tell that this looks like a horizontal line. Okay, hence the name horizontal asymptote. Sorry, horizontal tangent line. In general, though, just to be clear, something like this, a sharp point, doesn't happen in physics. All right, so normally that's not going to happen in physics. So that would imply you have basically you change directions in no time. But if you have more questions about that, you can ask me. Alright, another one, if a function has a vertical tangent, then it's not differentiable. Okay, so right here, notice that right here, if I were to ask you for the tangent line, this would be a vertical tangent line. And if you have a vertical tangent line, then it's also not differentiable at x is equal to 0. Okay, so let's do a few examples here. So if we have the graph G on this one, alright, you gotta tell me why this is not differentiable and at which point. So let's talk about what's not differentiable. Okay, so something that's not differentiable. Let's see, at x is equal to -1, right here, at that point, because we have a sharp point, we can say that x is not differentiable at x is equal to -1 because there's a cusp. The definition of a cusp is basically when you would have two oval shape or circles put together and it makes this little sharp peak right here, okay? Now it's also not differentiable at x is equal to 2 because at x is equal to 2, right here, you have a discontinuity. So this is discontinuous. Okay. At x is equal to 6, which is, let's see, 2, 3, 4, 5, 6, right here, you also have a cusp. Right, notice that you have that really sharp peak looking thing, alright? That's the definition where you have two circles put together. It makes that sharp appear. That sharp point appear. Right, finally, if you have, notice that right here, you have a vertical tangent line, and that's located at 7, 8, 9, 10, 11, right? So at x is equal to 11, you have a vertical tangent. And if I have a vertical tangent, then therefore is not differentiable at that point. Okay? Now, on example 2, what you're going to have to do, without graphing this, so without having to graph this, what you're going to have to do is you're going to have to find the derivative from the left and the right. Okay, so you're going to have to find that. Now remember, to find the derivative, we're going to have to use this formula. I'm going to write it up here so I have a little bit more room. So the derivative at a point in this instance at x is equal to 2 would be equal to the limit as x approaches c of f of x minus f of c all over x minus c. All right, so we're going to take the limit from the left and from the right. Now this is the same thing as taking the derivative from the left and from the right. Okay, so right now we're going to take the limit. Well, let's first find something out. Okay, so we have f of 2, we're going to need that point eventually, and f of 2 is equal to 5. Notice that if this was different, then you can kind of stop right there and it says discontinuous at x is equal to 2, and if it's discontinuous, then u is not differentiable at x is equal to 2. However, because you have the same thing here, then we're going to have to take those derivatives, right? Mainly, this is almost the same thing really as telling me if something is continuous if I take the derivative from the left and the derivative from the right. So in this one right here, we have the limit as x approaches 2 from the left. We have x squared plus 1. So remember that's f of x minus f of 2. F of 2 is 5 over x minus 2. Alright, then we're supposed to solve for that. So at this point I would have the limit as x approaches 2 from the left is x squared minus 4 over x minus 2. Okay, so we keep going. We can factor the top to x plus 2, x minus 2 over x minus 2. That's going to cancel. Now I can plug in my limit. I'm just going to plug in a 2. So my limit is 4. Alright, which means that the slope at that point is 4. Right? So notice that the difference here, instead of just taking the limit from the left and from the right, is that this right here shows me that the slope is 4 on that side. Okay? Now, I'm going to find the limit from the left. Now notice that I know which one's right and left, because if this is less than 2 right here, right, less than 2 is going to be from the left. So sorry, I should have written this here. This is from the left side. Now this right here, because that's greater than 2, that's going to be to the right of x. Of x is equal to 2, right? So to the right of x is equal to 2, that's going to be the derivative from the right. So we're going to say, I'm just going to write here from the right. Alright, so we have the derivative at 2 is equal to the limit as x approaches 2 from the right side of 4x minus 3 minus 5 over x minus 2. So again, this is f of x right here. This is f of c, and this is x minus c. Alright. So same thing here. We're going to try to simplify this. So we have 4x minus 8 over x minus 2. Then we're going to factor out 4 out of the top. So we have x minus 2 here, x minus 2 here. That's going to cancel that. So I end up with the limit as x approaches 2 from the right, which is the same thing as, in this case, the derivative at 2 is equal to 4. Alright, so notice that on this one, from the left and from the right, I'm approaching the same point. Or to be precise, the limit from the left and from the right is the same. So therefore, it's differentiable at 2. Alright, so I'm going to write this over here. So the left and right derivatives so one-sided limits here, that's the same thing. are equal. Therefore, remember those four little dots means therefore, f of x is differentiable at x is equal to 2. Alright, so in conclusion, if you have a piecewise defined function like this, then you're going to have to find the derivative from the left and the derivative from the right. And if those two numbers match, then it's differentiable at that point. Alright, if they don't match, well, then it's not differentiable. Alright, if you have any questions, please let me know. We'll see you next time.